Greetings and welcome, friends. We're talking today about the factor theorem. It's going to be amazing. It's kind of buddies with the remainder theorem that we talked about the other day. But let's take a look at this. I'm just going to jump right into a problem. Let's say I wanted to divide synthetically the following. Right? Let's say I have f of x equals x to the fourth plus x cubed minus 13x squared. Man, I'm like writing at a slope here. 13x squared. And I don't know, minus 25x minus 12. How about? And I want to divide that by the following. How about x minus 4? All right, so let's do that. And let's do the setup, the classic. So if I'm dividing by x minus 4, what's going in the box?
4.
Positive 4. And let's see, do I have any placeholders representing? No, it looks like I'm going to have 1, 1, negative 13, negative 25, and negative 12 friends. So here we go. Let's see what we got. So add, multiply. 1, 4, 5, 20, 7, 28, 3, 12, 0. What? So, it's kind of interesting. Let's translate this into a quotient. I guess I could even call it q of x or whatever if we wanted. What would q of x have been? X to the third, it'd be 1 degree less than the fourth, right? Because I divided by a linear. Plus 5x squared plus save an x and plus 3, right? There we go. And if I was to write it in that dividend equals quotient times divisor plus remainder form, I would have had the following, right? I would have had x to the fourth plus x cubed. That looks like a t there. That's fine. Minus 13x squared minus 25x minus 12 equals, and then I'd have the quotient, x cubed plus 5x squared plus 7x plus 3 times, let's see, the divisor, right, x minus 4. And then what's the remainder? Plus 0. So plus 0, I actually don't even have to write. Now look at my statements here on the left and on the right side of that equal sign. It appears as though I have partially factored that expression, right? It means x minus 4 divided evenly into that polynomial, right? Because its remainder was 0. You guys agree? Right? It divides in evenly. So additionally, I could say that anytime the remainder is 0, not only does x minus 4 divide in evenly, but it's also a factor of the polynomial. Because notice, right, this times this is equal to that. So that means x minus 4 is one of its factors. And let's see if I can actually write down the factor theorem. The factor theorem. All right, here we go. Write in words what we're going to do. Here we go. The binomial x minus a is a factor of the polynomial that's like the grossest f I've ever seen. I mean, right, guys? Like, ew, look at that. This f right here? Yeah. That's pretty gross. Of the polynomial f of x, if and only if, I don't know, have you guys ever heard the phrase if and only if?
Yes.
F of a equals 0. This, my friends, is the factor theorem. Here we are. If and only if means that this statement is true both ways. Is the word biconditional? It's a biconditional statement. I think that's the one back in the day when I taught geometry years ago. Basically, I could start with the if on this end and then get the beginning. My hypothesis and conclusion are interchangeable, and it's equally true. So if it's a factor, then the remainder is 0. All right? And likewise, if the remainder is 0, then it's a factor. Right? F of a equals 0. Of course, I'm referring to the remainder. But that also means, from what we learned about the remainder theorem, is that if the remainder is 0, that's also the value of the function when I plug in a. All right, all sorts of weird connections going on today. Bless you, friend. So I just want to point out that, okay, so if this is a factor of the original polynomial, then this guy actually has the remaining factors within it. So if I could learn how to factor this expression further, I would be able to eventually factor this entire thing. And what is the value of factors regarding polynomial functions? Well, you might recall back in the days of graphing quadratics that if I set a quadratic function equal to 0 and I could factor it, what was I able to find? The roots, right, or the x-intercepts or the zeros are all the same thing. So it would be beneficial for me to eventually be able to find the x-intercepts of a polynomial function as well. Find out where it crosses the x-axis, right? So lots of different benefits end up coming out of this. Now, little other definition fact. When you divide... I'll say it out loud then, sorry. When you divide a polynomial by one of its factors, the book specifies one of its binomial factors. I guess I'd say it, well, no, even if you divide by like some quadratic trinomial, it's still going to give you a depressed polynomial. By one of its, I'll just say its factors. Then the quotient is called a depressed polynomial. Aw. It's okay, don't worry about it. It's going to be fine. Here we go. Now, let me demonstrate this for us generically. So this ends up actually being really powerful for us to be able to solve for x-intercepts later. And this is a relationship that you wouldn't necessarily have assumed. So here we go. I've got this graph. You don't have to draw this. And I've got up top, I've got some sort of polynomial function up to a 4th degree, apparently. And I've got different sliders. So if I make a 0, then what's the degree of the function? Well, 0x to the 4th is 0, so then it would be a cubic function, right? And then I could even make this 0, and now the first two terms are 0, so now it's just a quadratic, and things like that. But check this out. If I have this quadratic function, this one happens to be 6x squared minus x minus 1, all right, is this purple parabola right here, right? And this orange dotted line, what does it have in common with that parabola? Yeah, it shares one of its x-intercepts. And notice where this orange line comes from is actually, it's this function g of x here, all right? And where I got g of x, I said, take your original function, whatever this guy is, and divide by one of its factors, right? X minus one of these x-intercepts would have been one of the factors here. Clearly, one of the x-intercepts occurred 3 times, but whatever. And so the function arose from dividing by one of its factors, and notice that it shares the other x-intercepts with it. So let's go back to when we had some other crazy ones. Here we are. So here I've got a third degree polynomial as the purple one. Actually, let me even change this graph to rectangular, just so I can better show you what's going on here. So here's actually based off of that end behavior, you guys immediately would have told me that it was a negative leading coefficient odd degree polynomial, I'm sure, based off of our Simon Says activity from earlier. So notice that how many x-intercepts can a third degree function have?
2.
2. Nope. 3. 3, right? As many as 3. It could have 2, right? For instance, if I shift this up, I could have had 2 right there. Or I could have had 1, right, if I shift that up and stuff. So you can kind of see a couple occurring there. But notice the orange graph. It is 1 degree less because I've divided it by a linear binomial. And notice, what does the graph have in common with my original purple graph? It shares 2 of the x-intercepts. All right? So this is the big idea, is a depressed polynomial. All right? When you divide by one of your factors, you get a depressed polynomial. The depressed polynomial will have the 2 other, or whatever number of remaining x-intercepts hidden within it. Okay? Is the idea. So watch, let's actually go to a 4th degree for the first one. Let's see if I can actually get this to work. There we go. There's an ugly 4th degree. And let's shift it up so we actually have 4 x-intercepts. There. Bam. So now I've got K, L, M, and N, right? There's my x-intercepts, right? And notice what I have. If I divide by x plus 3, all right, x minus a negative 3 is plus 3. If I divide by the binomial factor that gave me the k, the depressed polynomial ends up having the 3 remaining x-intercepts built within it. So what this means is if I can find factors over time, I can keep getting depressed and then more depressed and more depressed polynomials. Don't worry, I'm fine. I'm very positive about life. I'm not getting more depressed. Just my polynomials that I'm solving are. But I could actually end up like finding all of the x-intercepts over time.
You're like the psychologist, and like you have a lot of patients that are depressed, and you have to help them find their way.
Yeah, sure, there you go. So yeah, no matter where these land, let's see, can I get some interesting shapes on this? Yeah, as I slide it, I get some different results.
What if you put them all at 6?
It looks like slime.
Right, so there's 4 x-intercepts, and notice the depressed polynomial, negative 2.48 is where k is occurring. So if I divide my original polynomial by x plus 2.48, I end up getting a depressed polynomial, and what does it have? It shares all of the other x-intercepts that I'm missing. So it's kind of like this interesting little relationship. Question, comment?
Did you write that formula down?
No. Oh, we're good. We're gonna do some actual examples. And actually, before we even do that, let's do our own sketch of the problem we just did. All right. So I'm gonna graph. You guys don't have to sketch this. Just follow along. Just learn. That's good. So let's see. What did we do for our startup problem? We had a 4th degree polynomial, right? We had x to the 4th. Plus x cubed, what was it? Minus 16x or something like that? Minus 13x squared, minus 25x, minus 12. All right, so here's my original polynomial. All right, let me actually, I'll make it a little bit more visible to our online friends. All right, so there's the original polynomial we had, and I'll make it a rectangular grid, so I'll smoosh it in one direction just for visibility's sake. So you can see that it had kind of the classic, up to 3 bends of a polynomial, right? And what did we find? We divided by x minus 4, right? And when we did that, we found out that it went in this many times. So this q of x I could have referred to as my depressed polynomial. let's graph the depressed polynomial and see what it has in common with the other one. Now, x minus 4 would have had, x minus 4 represented which x-intercept in this graph? It looks like I've got 3 of them. I had one occur at -3, I had one occur at -1, twice technically, and I have one occur at +4. So x minus 4, if I set that equal to 0 to solve after factoring, would have given me the +4 x-intercept, right? You guys agree? Right, so that's the one I had. So let's see if my depressed polynomial will actually share these remaining 2. All right, so let's graph x cubed plus 5x squared, x to the third plus 5x squared. Come on here, help me out. Plus 7x plus 3. Yeah, thank you. So when I graph this, where do I expect it to cross the x-axis? -3 and -1. Let's see what happens. Bam. Wow. What do you know? No, just follow along. Observe, learn, enjoy. Color, we'll make this orange. We'll make it medium. We'll also make it, how about dashed? There we go. So you can see that the depressed polynomial actually contains the other x-intercepts. Now, actually, oh, this might be valuable. Valuable. Aha! Guys, you know what? This depressed polynomial will actually have other depressed polynomials within it. Insanity. Insanity here. All right. So looking at this example, you don't have to write this down. We're gonna, don't draw it, but you can write it down. So if I have this g of x function, my depressed polynomial, right? I expect that it has a couple of these x-intercepts. This one I'm thinking occurs twice because it ricochets off the graph. Let's see. Let's actually get rid of one of these. This occurs at -1. You guys agree? So for g of x, let's see. Here we go. For g of x, comma -1 is an x-intercept. So if -1 is an x-intercept, what do you think a binomial factor of that would have been? Therefore, x with a what would have been the factor? X plus 1. Remember, just like with synthetic division, it was always the opposite. Right, same idea here. So therefore, x plus 1 is a factor. So let's divide g of x by x plus 1, and that should give me another depressed polynomial that should have this x-intercept remaining in it, and probably one more of those. That one's going to occur twice, I believe. So let's divide g of x. So g of x divided by x plus 1, I would have a -1 in there. So we can write down from this part 1, 5, 7, 3. Now, the fact that I'm expecting this to give me an x-intercept, that I'm expecting this to divide in evenly, my question for you is, what do I anticipate my remainder for this to be? And it has to be 0.
Yeah.
If -1 is an x-intercept, and if x plus 1 is a factor, then this must equal 0. That's the only way for this to work out. So I'm risking a lot on this problem. Here we go. Let's hope it works out. So let's do this. Add. All right, I'm scared, guys. Multiply. Add. Multiply. Add. What? Represent, friends. Check it out. Can you believe it? How great is that? It worked out. So question. What is an even further depressed polynomial h of x? He's got way more problems than g of x ever thought he had. He's like super depressed. He's like, why does g of x and f of x have so many x-intercepts? I'm only going to have 2. And it's all like sad on itself. H of x, stop comparing yourself to the other 2. You'll be fine. Seriously, don't worry, h of x. You're special. You're a quadratic, in fact. That's pretty great. Right? So, I'm sorry. I'm just trying to cheer him up. So based off of this, what would h of x be?
1 x squared plus 4x plus 3.
I agree. And let's graph this just for funsies. Here we go. Graph x squared, 1x squared, plus 4x plus 3, right? Now, this is going to be a parabola. What do you think its x-intercepts are going to be? -3 and -1. Let's graph this. What do you know, guys? Look at that. What? Isn't that crazy? It shares the x-intercepts with it because it had them all along. It's what they have in common.
Should we go farther and be like,
Yeah, let's go even further. Why not? I like your thinking. Let's make that one blue. So, I'll even grab a snapshot of this. It's a thing of beauty. I'm going to Snapchat this. Here we go. What's funny is, like, 5 years from now, people are going to watch this video learning math about depressed polynomials, and they'll be like, what's Snapchat? Isn't that funny? That's funny. I think it's funny. So for this blue parabola, all right, it looks like it has two x-intercepts. It looks like one occurs there. Let's see, let me pick a darker color here. It looks like one occurs at -3 and one occurs at, oh, squeaky shoes, -1. All right, do you guys agree?
Yeah.
So which one do you want to divide by? Which one do you want to get rid of first? The -1? Sure. So if -1 is an x-intercept, then what is a factor? Then x plus 1 is a factor, right? So let's divide h of x by x plus 1. All right, I'm going to let you guys just write that down real quick before I slide on over. So let's see, x squared plus 4x plus 3. Also, I just want to point out, I actually could find the factors of this without doing synthetic division and everything. How could I do that? Well, we actually are really good. You guys are really good at factoring quadratics. And I suspect that this one's factorable because these look like those are going to be rational answers. So it should be factorable. But let's do this. X squared plus 4x plus 3. So h of x equals x squared plus 4x plus 3. And I'm going to divide by x plus 1 because x minus 1 was the x-intercept. So let's do this. So -1 is going to go in the box. Bam. 1, 4, 3. So question, what's the remainder going to be? 0, are you sure?
Yes.
Right? And it has to be 0 because if this is truly a factor, then that means it must divide into this an even number of times. There would be no remainder left over, right? So that's what the whole idea behind the factor theorem is. So let's do this. I'm worried. Bring down, add, multiply, and it works out. Crazy sauce. Let's see, who's even more depressed than h of x? You're depressed? I am depressed? Oh, man, that's sad. Let's see, I of x. I guess I could have j. I don't know, I looks too imaginary. Nah, we'll do I of x.
Oh, now my clothes go back to the technical.
So, I of x is equal to what now? Yeah, x plus 3. Okay. You guys know how to graph a line? What's the slope of that? 1 over 1. This y-intercept is 3. All right. Do you know its x-intercept? It's going to be at the -3 here. Let's graph this. X plus 3. Ready? Ready? Bam. What? Guys, isn't this crazy? I think it's crazy. Let's see. I'm going to make this one a dotted line, not even a dashed, because it's the most depressed. Let's see. What's a good color for this one? Red? Okay. There we go. So yeah, notice, wow, isn't that cool? Actually, that's really intriguing. These ones happen to share a y-intercept as well. That, I don't believe, should often happen. Wow, I actually like the way that animates when I scale it. It looks like ants, like, on parade.
It's like, it has the illusion of being.
So let me grab a snapshot of this, and this is just beautiful, friends.
That's beautiful. That's like life.
Yeah. Yeah, we don't have to be depressed at all. Right? Look at this. Thing of beauty, thing of beauty. So notice x plus 3 has the remaining x-intercept. If I wanted to solve for that x-intercept, what could I do? I could just set the function equal to 0 and solve. Let's do that for fun. X plus 3 equals 0. Yeah, x equals negative 3. Bam. Right? So I can actually, with these skills, we're going to be able to find the x-intercepts of polynomial functions. All right? As long as we have a decent way of finding kind of the depressed polynomial stuff. Now, on tonight's homework, they're actually going to give you like a starter one where they're going to be like, okay, so here's a polynomial and here's one of its factors. Start finding the depressed polynomials and the other factors. So they'll give you one for starters. And I wouldn't, actually, it would be cool if you could graph. I'm sure if you look online, there's probably some graphing technology calculator websites out there where you could just plug in your functions and guess some of your x-intercepts if you don't have a graphing calculator, if you wanted to have that visual assistance. But this is the idea. If I have an x-intercept, then I know a factor. If I have a factor and divide by it, I expect its remainder to be 0. And the quotient is going to be a depressed polynomial that contains the other x-intercepts, the other roots that I'm looking for. Isn't it great? Look at that graph. That graph looks awesome. Wow. Well, anyways, thanks for watching, Internet friends.
Thank you. Have a great day. Don't be depressed.
Oh, very good advice. Very good advice. Bye-bye.